That's a bit late to record, like, okay. So in the beginning, we did classical thermodynamics, and as I told you, thermodynamics just kind of builds relations, right? You get this sort of weird stuff like that ds dp. I mean, you're totally sick and tired of this, right? But now you know that ds dp is plus or minus dv dt, right? So it relates all these things, and that can be very useful. And I'll give you a useful one that I never derived for you, because it will make a connection to stat mech. Let's say I want to know really what thermal expansion deep down is, right? dV dt at constant P. Well, I can relate that to dV with a minus sign, ds dp, right? Through that Maxwell relation I did. And then I do, chain rule, blah, blah, blah. And basically what I'll find is that alpha V is beta T ds dV at constant T. So this is sort of an example of how thermodynamics is useful, right? Let's say you want to know thermal expansion. It would be very hard to do that from, say, quantum mechanics. Like, you would have to simulate a system and figure out how under constant pressure it expands, which is sort of really hard. But thermodynamics tells you that it's actually the source of thermal expansion is the change of entropy with volume. So if a material gets higher entropy with higher volume, then it has a positive thermal expansion. And statistical mechanics is going to teach us how to calculate these things, how to calculate entropy, and then we can do it either at different volume or take its derivative. And you'll see later then why that implies that in many cases, thermal expansion is positive. So again, right, thermodynamics build this relation, and then statistical mechanics is going to give you the input to these quantities that we need to calculate. So what kind of questions will thermodynamics answer? Oh, my equations are gone. Well, let's see how well I know them so I can fill them in. There were supposed to be equations on here. So the different perspective between thermodynamics between thermodynamics and statistical mechanics is that in thermodynamics, when we look at equilibrium, it's a static thing, right? Things go to an equilibrium state and then they stay there. In macroscopic language, the equilibrium state is static. You know that in the microscopic view of matter, that's not true. If I take a box of gas molecules and I let that equilibrate, yes, the volume or the pressure, depending on what I constrain, comes to an equilibrium. But in reality, the internal state of that system is constantly changing. Gas molecules fluctuate around, move around. The same is true with atoms, right? They vibrate around. In some cases, they even hop around, even in an equilibrium state. So the fundamental difference is that in thermodynamics, the equilibrium state is static. In a microscopic view, the equilibrium state is dynamic. Right? It fluctuates. So we have to build a relation between these fluctuating quantities and the static quantities. So we're going to do that, and we're going to find that in many cases, it's actually quite simple. And I was supposed to write this here. In many cases, what we'll call the mechanical extensive variables, and I'll come to that, explain that better, are simply time averages. So if I want to know say what the internal energy is, the internal energy of a system is simply the time average of the fluctuating energy. So I'm going to use, in many cases, brackets like this to denote averages, right? So you could, let's say you actually knew that energy trajectory, you could write that out more formally, right? It's the limit of t going to infinity, 1 over t, the integral from 0 to t, et dt. And I've kind of messed up limits here and dummy variables are all mixed in together, right? And the same would be true for volume, polarization. So if I have a system under constant pressure, its volume would slightly fluctuate in time. And the macroscopic volume, the equilibrium volume, is simply the average volume. The only thing that's fundamentally different is entropy. Entropy is not an average because entropy does not exist at the microscopic level. That will be the conclusion we come to. Entropy is not something you average, but entropy will be a fundamental quantity of the fluctuations themselves. So we will find later Well, we won't find it. We will postulate that the entropy is some constant, which is the Boltzmann constant, of the logarithm. So this is as a function of u, of the logarithm of omega, and omega will be the number of microscopic states with energy u. Microscopic, there we go, states. So energy is fundamentally different, right? This is not an averaging. And I want to show you something that I think is quite cool. And I'm going to get a new slide for that. Okay. So if I write thermodynamic potentials in the entropy formalism, right? I write ds is 1 over T du minus some I xi over T dxi. And I put that together with the statistical mechanics statements of the entropy. When I'm saying I'm maximizing S, I'm maximizing S here under a given, essentially a given set of energy constraints, right? This is really what I'm doing here is I have a certain amount of internal energy and then I count here the potential energy. When I'm saying I'm maximizing S, what am I really maximizing? What I'm really maximizing is omega, right? And what is omega? Omega is the number of ways, will be the multiplicity, the number of ways a system can appear with that energy. So it turns out that maximum entropy in thermodynamics will simply be maximization of appearances. Like what you see macroscopically is the thing that has the most microscopic realizations. And I'm giving you a preview here, right? This is not the short version of the lecture. Well, this is the short version of the lecture, but you're going to get the long version. So don't worry if you don't get it, but I want to give you the arch that we're going to span. So in some sense, entropy is what truly makes the link between the macroscopic and the microscopic. Let me go back now to the lecture notes. Oh, I was supposed to write this here. Okay. So once we can make this relation between microscopic statements, things about energetics and so, we will be able to formally actually calculate things. And again, we were not able to do this in thermodynamics, right? Because thermodynamics has no microscopic input. So for example, we'll be able to calculate heat capacities of things. Here's the one for silver. We will show what the slope is, how this looks like near zero. We will show what the limiting values are. If you go further, which we will only tangentially touch upon, you will be able to calculate the topology of phase diagrams. Here's, for example, the gold-copper phase diagram. It has sort of a disordered FCC here, and then it has all kinds of ordered phases here. And statistical mechanics will show us how we could get this by linking to quantum mechanics to get the interactions between species, and then actually get the thermodynamics. You would get the free energies, and then ultimately the phase diagram. And that is actually done today, right? And this is sort of my original field, that through statistical mechanics, you can actually link quantum mechanics, which allows you to get information about systems as they call ab initio without any input except the atomic numbers. You can connect now quantum mechanics all the way to thermodynamics. We're not going to do that in this course because it's a bit too involved, but you really wouldn't be able to do that if you didn't have the statistical mechanics links. So that allows us today to calculate things as what is called ab initio, right? We can start from quantum mechanics, go through statistical mechanics, and get true thermodynamic quantities, things like Gibbs free energies, heat capacities, and therefore we can actually predict phase stability, phase diagrams, etc. Okay. So that's kind of the end of my motivational speech. I hope you're all riled up for this super exciting topic. Okay, let's go back to the board. So let you give me the outline. So most of the time we're going to focus on what are called mechanical variables. And these are things like the energy, the extensive quantities, xi, because in statistical mechanics, these are time averages. So it's in some sense the most simple relation you can imagine between the microscopic and the macroscopic world. Like you just observe them over time, and the time average is the macroscopic quantity. So if we wanted to do this in practice, what would we need? So what is needed? Because this is all good and well to say, but how do you do this in practice, right? So the first thing we would need to know is, how would we do the averaging? And in principle, you could simply do the time integral. So let me write that one down again. So let's say I could track the energy, and I average over some time interval, right? I mean, I wouldn't be able to go to infinity, but this would give me the time average of the energy. The problem is that if I want to simulate or calculate a system in time, I need its dynamics. I literally would need to know how the atoms interact and their equations of motion and everything. And that's actually not particularly practical. And statistical mechanics will tell you that you can get the time averages without the dynamics. So while you could do it this way, if you had the dynamics, this is not how we're going to do it because it's way too hard. And the fundamental principle here is that we will replace a time average by what's called an ensemble average. And we'll have a formal definition of ensemble later, but for now, think of an ensemble as simply all the microscopic states you can be in, right? You have a system in a box, particles in a box, whatever. This is really all the possible microscopic states. So I write microscopic with a mu. No, I don't, because I can't spell. Microscopic. The second thing, though, that we need, if we want to do that averaging, and we do not do it as a time average, we do it as an ensemble average, we need the probability that a system spends in each microscopic states. So the probability that a system occupies a given microscopic state. So that's the second thing we need. The third thing we need is a proper definition of which states do we average over. That's basically saying what is the ensemble. So which states to average over. And that will link us to quantum mechanics, because formally the states to average over are the quantum eigenstates of the system. So this comes from quantum mechanics. In practice, we will be a little less rigorous here. So maybe not always eigenstates. Okay, then what else do we need to do? After we do the averaging, we will relate all the averages to thermodynamic quantities. In many cases, that will be obvious, right? Like time averages. But for things like entropy and things that have potentials that have entropy in them, like Gibbs free energy, Helmholtz free energy, that will be a little more complicated. And then we will do some examples. And that's basically the outline of the statistical mechanics lectures. Okay, so how to do the averaging, getting probabilities, defining the ensemble, and relation to thermodynamic quantities, and you can't see anything of what I'm pointing at. There we go, camera, here you go. And then we do some examples, and that's it. So let me start with number 3 here, really. What are the states? So the possible microstates they are all the solutions to the Schrödinger equation of the system. So they are the eigenstates. And if that gets the fear of God in you, don't worry, we won't be solving many quantum mechanics problems here. We will be limited to particle in a box. So remember the general Schrödinger problem, right? Is that you're looking for a wave function that describes your system. And the way you do that is by looking for the eigenstates of this problem. The Hamiltonian, so the Hamiltonian operating on the wave function has to return the energy of the system times the wave function again, right? So if that is satisfied, then psi here is an eigenstate. How does a typical Hamiltonian look like for a material in quantum mechanics? Well, there's always a kinetic energy operator, right? That's the del squared operator, so minus h squared over 2m. And the kinetic energy operator is the curvature of the wave function. So it's d squared dx squared plus d squared dy squared plus d squared dz squared, right? Measures curvature of the wave function. So that's the kinetic energy operator. And then in general, there is a interaction term, which I'll call, problem is we don't have good symbols, I'll call it V, but V isn't really volume here, which also depends on the coordinates. I've written this here in one coordinate, so you could think of the coordinate of one particle. But of course, if we do this on a many body system, or a system with many particles, many electrons, many atoms, then this is basically, there's a term like this for every coordinate, right? So this is a massive problem, right? So when you solve this, if you could, what do solutions give you? So how do solutions look like? You would get a bunch of eigenstates, right? Psi I. These are the states the system can be in. The eigenstates would have an energy. And that would be the energy of the system when it's in that state. And in some cases, we would manipulate that a bit and get what's called a degeneracy. And I'll come back to this later. This would be the degeneracy. So how many states there are? Degeneracy of EI. So this would be a measure of how many states there are with that energy. So as you know what, right, from quantum mechanics, states are discrete. In some cases, you will see that discreteness in macroscopic observations, and we'll show some examples, and heat capacity will be a good example of that. But in other cases, you will not see the discreteness. And the reason is that in some cases, these energy states will become so close together that they will look like a continuum. And then the energy spectrum of a system will look like a continuum, which is just like classical mechanics, right? If I take a particle in a potential and I can have any position, any kinetic energy, then the energy spectrum of that particle is continuous, right? I can take on any value. In quantum mechanics, an energy spectrum is not continuous, but in some cases, it will look continuous. And I'll distinguish those a bit later. So I want to do a couple of examples. Let me go back to sharing. Sharing is good. Sorry, I did something wrong. I have my coffee next to my computer, which is a recipe for disaster in one of the lectures to come, I'm sure. Okay, so let's do the particle in a box as an example. We're going to do a one-dimensional box as good physicists, right? So here's my box. The length here is A. And what does a particle in a box mean? What it really means that in here, say, the potential is 0. Oops, sorry. So in here, the potential is 0, and these walls are infinitely high, so outside the potential is infinite, right? That's really what a particle in a box means. So the particle we want to be mostly confined to being inside the box. So all you have is the kinetic energy operator now, because the potential is 0. So this is a problem you can solve exactly. And you find that there are a bunch of energy levels, which are given here, En, where n appears here. And the spacing of the energy level is this object here, right? So it always has some, depending on whether you use h bar or h, it tends to have pi in it, and h bar, because h bar is the fundamental quantum mechanical unit, it usually scales inversely with the mass, and here it also scales inversely with a squared. Okay, so if you actually look at the states, let's pick out n equals 1 here. So this is the box here, and this is the state n equals 1. So if you actually plotted the wave function, that would be the lowest energy wave function. So when n equals 1, you get this energy here. If you look at n equals 2, it's this, what do you call that? Mauve, pink, this thing here. right? So it has more curvature. If I go to n equals 4, right, I got this guy here. So the larger n becomes, the more oscillations I get in the wave function, so the higher the kinetic energy of my system, right? Because this operator is the kinetic energy operator. I'm essentially adding up all the curvature of the system. So a few things to observe here that are maybe a little odd. The energy is actually never zero. So the lowest energy state you can be in is actually not zero. It's this quantum here, pi squared h squared over 2ma squared. Now obviously as your box gets big, as this A gets big, this lowest energy state tends to go to zero, but it's never zero. Okay. The other thing you should realize is that, maybe not for this class, but in general, kinetic energy measures the curvature of the wave function. And let me digress here a little, because this might be useful in your general understanding of bonding and quantum mechanics. You often think of a localized electron state as having low kinetic energy, right? Because it's localized, versus a delocalized electron state like in a metal, you would think has high kinetic energy because it goes everywhere, but it's actually the opposite, right? If you have a delocalized wave function, one that sort of goes everywhere, slowly varies, that actually has low kinetic energy. If you make a localized bond, right, you actually have like a core electron, you actually have high kinetic energy. So it's maybe just the opposite of what you think about, right? And by the way, this is why metals form, right? The reason that metals form is because the electron wave function can delocalize, so the electrons really bring down their kinetic energy. So delocalization for electrons is good, unlike for your studies. Okay, that was a good joke. Should have laughed. Okay, and the degeneracy for each level here is 1. So there's only one energy at each level. So, because there's only one state for each n. Okay. So that's the particle in a box, and we'll come back to that. You already know how this class is going to go, right? How many problems can you solve in quantum mechanics, right? You can solve the particle in a box. You can solve the harmonic oscillator. And I don't know if I'm forgetting any, and I'm going to show you the solutions to these. They are actually quite relevant to materials. So the other one is the harmonic oscillator, which you can sort of imagine is something that moves in a periodic potential. So the macroscopic image of that, of course, the macroscopic picture of that is a spring, right? If I have a ball that moves on a spring and the potential energy of the spring is harmonic, so it goes like the cube of the displacement. So somehow I measure displacement here. That's called the harmonic potential. So the harmonic oscillator is kind of representative of all harmonic problems. So even in quantum mechanics, if your potential energy behaves like the square of the displacement coordinates, it would be called harmonic. Again, you can solve that because now the Hamiltonian actually has energy in it, potential energy in it, right? So now what does the Hamiltonian look like? It looks like H is minus H bar squared over 2m times d dx squared, right? That's the kinetic energy operator, is always there. But now I also have plus 1/2 kx squared, right? That's my Hamiltonian now. You could actually look for the eigenfunctions and the eigensolutions of that, so solve the eigenvalue problem. And what you would find is that you have this energy levels. And by the way, the wave functions are shown here in case you care. I mean, again, right, the lower ones have no nodes. This is the lowest energy. And again, this is what you expect, right? This is the lowest wave function. Most of the density is in the minimum of the potential, but there is some density that goes to larger energies, right? And then the first excited wave function here is the one where the thing starts to oscillate in the potential, right? It spends some time here, it spends some time there, right? It looks a little like what you would expect classical, right? Okay, so The energy states now go like n plus 1/2 h omega, where omega is the frequency. It's the natural frequency of the oscillator. So typically omega is something like the square root of a force constant k divided by the mass. So if a spring or a potential is stiffer, you get a higher frequency. If the weight hanging of it is higher, you get a lower frequency, right? Those are the concepts you got to remember, because later we're going to map this onto vibrations in atoms, right? So the sequence that you're going to have to remember, and not just today, we'll come back on it. If I'm stiff, you know, if I have a stiff frequency, a stiff force constant, the frequency goes up. That means that the energy level separation goes up. So soft bonds, small spacing of energy levels, stiff bonds, large separation of energy levels. Okay. Again, though, you find this cool thing that the energy is never zero, because N0 is the lowest state, but even for N0, you have energy 1/2 h bar omega. And this is what's referred to as the 0-point motion. Unlike in the particle in a box, the spacing between the energy levels here, it's fixed. It's the same quantum every time. And the reason is that you have n here as the quantum number, whereas before we had n squared. So we had unequal spacing. Okay. So that's it. That is the two problems you can solve in quantum mechanics, like exactly, well, there's a few more, but the two that we care about. In most quantum mechanical systems, you can obviously not solve them exactly. And for real materials, you have to go through all kinds of approximations to calculate the eigenstates. Having said that, there are certain approximations under which we can get a lot of useful information, even for what appears to be complicated systems. And we use a certain set of assumptions and principles for that, which I want to slowly walk through. And one of them is the many body problem as a sum of independent single body problems. So fasten your seatbelt and sharpen your eyes. There's a bit of math coming. So in many cases, we actually have a many body problem. And with many body, we just mean that we have a bunch of particles or degrees of freedom. And that makes it really hard to solve the Schrödinger equation for. But not in some approximations. So first I'm going to solve this when the many body problem is the sum of
you need to unshare your screen.
Oh, thank you. So when the many body problem is the sum of independent one body problems. You could also read this simply as many degrees of freedom, 1 degree of freedom, the degrees of freedom do not interact. That's really the problem I'm solving here, right? So formally in quantum mechanics, that means that the Hamiltonian is the sum of Hamiltonians of a bunch of degrees of freedom that don't mix. So I have H alpha plus H beta plus H gamma, where alpha, beta, and gamma refer to degrees of freedom, or they could be the subsystems. So let's say that I can solve each independent system, each one body problem. So the eigenvalues and eigenstates for each one body problem are known. So if I take Hj, I can solve that and sorry. So H, say, operating on psi j would give me epsilon j psi j. Well, if that's true, then I can actually solve the many-body problem. Because for a simple mathematical reason, if I take as a wave function psi for the total system, I really shouldn't call this defined, but I'm going to. I should. The assumption. I write it as the product of the single particle wave functions. Then I'll show it to you that psi is an eigenstate of the full Hamiltonian and that I know the eigenvalues of that. And the reason is that if I operate the Hamiltonian on psi, so what does that actually mean if I write that out? That means that I operate H alpha plus H beta plus H gamma. And I operate it now on the product wave function, psi alpha, psi beta, psi gamma. So if you take, for example, H alpha, when that operates on this product wave function, it only sees psi alpha because psi alpha is the only thing that has any coordinates in it that relate to the Hamiltonian in alpha. Psi beta, psi gamma, that is dependent on coordinates that do not belong to alpha. So they behave like a constant for H alpha. So a constant just moves through the operator. So it's in pink. So if I take this and I operate it on the wave function, the full wave function, so do not write in pink. So H alpha operating on the full wave function is equal to all the constant pieces shoved through, and then I get H operating on psi alpha. And this I know because this is the one particle eigenvalue problem. This is epsilon times psi alpha. So that means this is equal to epsilon alpha times the full wave function. So this is epsilon alpha times the full psi. So I can do this for every part of this Hamiltonian, and each time I will get the eigenvalue for that part of the Hamiltonian. So what does that mean? Come on, camera. You can learn. Come on, come down. Come on, come down. There you go. Okay. So what does that mean? That H times psi is epsilon alpha plus epsilon beta plus epsilon gamma plus blah, blah, blah times psi. So that means that the energy is epsilon alpha plus epsilon beta plus epsilon gamma. And the wave function psi is just the product wave function. You know, as always, don't get lost in the math, right? Take a step back and like, I hope this makes sense to you, right? I've told you that alpha, beta, and gamma are independent of each other. So what I'm telling you now is, hooray, that means the energy of the total system is just the sum of the energy of the subsystems. which you could have written down, right? Like, because I said they don't interact, so the energy just sums over all the subsystems. The wave function is a little more complicated, but you could sort of think your way through this, that what this really is a statement of is that the probability of a state in alpha, of whatever happens in alpha, is independent of what goes on in beta and gamma. So I could write this in words, but it would just be a way to make the lecture longer. Okay, I'll do this. When a system is composed of independent subsystems, then its possible energy states are the sum of the possible eigenstates of each degree of freedom. So basically, quantum mechanics is completely consistent with what we would expect. So maybe I should take a brief pause, like, what does it mean to be independent? So there is sort of the obvious way of being independent, right? Like, if I take a big box and I divide this in 4, and I call this part alpha, this part beta, this part gamma, this part delta, right? And I make sure you cannot interact across the boundaries of the box. So there's no energy transfer across the boundary of the box. There's no heat transfer. Then what I'm really saying is that, you know, well, what goes on in alpha has to be independent of what goes on in beta, and the total energy of my system has to be just E alpha plus E beta. This is required by extensivity of thermodynamics, right? That if I add subsystems together, but I don't let them interact, the energy just has to be the sum of the subsystems. This is essentially saying the same as conservation of energy, right? The fact that I just count them together shouldn't change them. But sometimes this independent degrees of freedom is more subtle. You know, this is sort of the obvious version, right? Version 2 is where they live in the same system. For example, you know, maybe you have a bunch of particles here, and it's possible that the particles don't interact, although we will later see that not interacting is a subtle statement. But it is possible that they have independent degrees of freedom. For example, let me give you an example of that. Maybe they have a kinetic energy degree of freedom, right? But let's say they carry a magnetic moment. Then if I apply the magnetic field, then that magnetic moment in the magnetic field could have multiple states, right? Like the spin could be up or down in the field. We could probably safely assume that that does not affect the kinetic energy of the particle, of the gas particle. So those will be two independent degrees of freedom. And what I would be saying is, you know, the total energy is the kinetic energy of a particle plus its energy in the magnetic field, right?
I had a question.
Yes.
So just above where you just were, why is big psi the sum of all, sorry, why is big psi the product of all the little psi's and not the sum?
Oh, it's just because of the way quantum mechanics works, right? So I postulated that actually here.
Okay.
Let's go back here, camera. So if you go back to how it's done in quantum mechanics, you postulate this as a trial wave function, and then you show that that's an eigenfunction, right?
Okay. Thank you.
And what you can already see is that there's many combinations right here, because there isn't just one wave function for alpha, right? Alpha has a spectrum of eigenstates. So there are many, many possible ways to mix the alpha and the beta and the gamma wave function, because each of the subsystem has many possible states. So there are actually many possible versions of this, right? Okay. So let me show you a degree of freedom that's in a system that's maybe not as obvious. So let's say I do particle in a box, but in 3 dimensions. So particle in a 3D box. So I'm going to make it, for simplicity, a cubic box. So all the dimensions are equal to A. So what's the Hamiltonian now? Well, now I can take up kinetic energy in 3 degrees of freedom. So the kinetic energy operator is now d dx squared plus d dy squared plus d dz squared. Now I argue that these are 3 independent degrees of freedom, because this measure of the curvature in the x direction has nothing to do with the y coordinate of the wave function, and etc. here and here. So a particle in a 3-dimensional box is like 3 particles in a 1-dimensional box, because I have 3 degrees of freedom that behave independently of each other. I can set the curvature in the y direction independent of the curvature in the x direction. And so you can solve this as the superposition, like we did there before, of 3 1-dimensional particle in a box problems. So that means that now I have 3 quantum numbers. So the energy now depends on an x quantum number, a y quantum number, and a z quantum number, which measures the state, right? The energy level I'm in the x, y, and z direction, which is h squared over 2 ma squared nx squared plus ny squared plus nz squared. And now there are many ways to get a certain energy, right? Because the total energy now depends on the sum of these quantum numbers. So I could make a table here of like possible states, right? nx, ny, nz. For example, if I do 1, 1, 2, or I do 2, 1, 1, or I do 1, 2, 1. These are different quantum states, but they sum to the same energy, right? So whenever this sum, which I'll call r squared, because you can think of it as a radius in a 3-dimensional space, when this is a certain value, I have the same energy. So this gets a much more interesting problem than the particle in a 1-dimensional box. And so to measure the number of states, we define a quantity called the density of states. And the density of states is formally defined as a derivative. So if I define psi epsilon, if I define this as the total number of states contained within this energy, so with energy less than this, so with energy less than or equal to epsilon, then the density of states is formally derived as the derivative. So the density of states epsilon is how that total number of states changes with energy. And this is the DOS, or density of states. Keep in mind the units here are something like, units here are number per energy, right? Density of states and degeneracy and multiplicity are often sort of confused, and I'll be honest with you, I confuse them sometimes too. But this is a measure, right? This is number per unit energy. So if you want to know the states in a certain energy range, what you would have to do is you would have to take omega epsilon times the epsilon, right? That would be the number of states in this infinitesimal energy range. And if you wanted them in a macroscopic energy range, like say from E min to E max, you would have to integrate this, right? That would be the number of states with energy between E min and E max. In statistical mechanics, we use all kinds of measures for density of states or degeneracy or multiplicity. So when I, like here, I could say the multiplicity. So what's the degeneracy of the state where the energy is, let's see, if I do 1, 1, so that's 4, 5. So the energy is 6. Well, 6 in these funky units, right? E is 6 times some weird unit. So the degeneracy or multiplicity here is 3, right? I have 3 states. This is 3. Degeneracy or multiplicity are simply numbers, right? They're not the same as the density of states, but we confuse them sometimes formally. So just be a little careful. This is a measure of, I mean, truly it's a density measure, right? How the number of states changes with energy. But they all kind of tell you the same thing. They're just a different way of counting in different units. Okay, let's calculate that in 3D. You know, this is a bit sort of, it's not difficult math, but you know, statistical mechanics, there's a lot of things that show up, and there's h squareds being dragged around and m's and a's, and that makes it a little messy. But try to kind of see the, I never get it, is the forest to the trees or the trees to the forest? I think it's the forest to the trees, right, that you have to see. Is that like, I think you need to see the forest through the trees, or is it the trees to the forest? Whatever, one of the two. Because this kind of derivation in some form or another is actually often done, and it's useful in a lot of parts of material science, not just statistical mechanics. So I want to calculate, and so many properties actually simply are determined by densities. You don't need to know much else. So I'm going to calculate this function here, the total number of states with energy. So basically, if I plot this in a 3-dimensional coordinate system, right, x, y, z, so I plot nx, ny, and z, then everything that lies on a sphere has the same energy, right? So everything that lies on a sphere has the same energy. It's actually only 1/8 of a sphere, right? Because the numbers n, the quantum numbers have to be positive, right? So I know the volume, the number of states in here is the volume of that sphere. So that means that what is the number of states up to a certain energy? It's 1/8 of the volume of that sphere. So it's 1/8 of 4 pi r cubed divided by 3, right? Volume of a sphere, I take 1/8 of it. I have r cubed here. I want to get this in terms of energy, but I know the relation, right? Because this is the relation here. Here I've written the energy in terms of r squared. So I'm just going to substitute energy for R with the appropriate powers. So if I plug in all the math, I get pi over 6, 8 ma squared times the energy over h squared. I think that's h and not h bar, but I got to check that. To the power 3/2. So that's the number of states in the up to that energy. So the density of states is the energy derivative of this. It's the phi e d epsilon. And before we do that, right, what's going to happen is that I have a bunch of prefactor which doesn't do anything when I take the derivative, but I have epsilon to the power 3/2. So that's going to become epsilon to the 1/2 when I take the derivative. So the density of states is going to go like the square root of energy. So let's look at that. There's a few important dependencies here, right? Density of states in 3-dimensional, a kinetic energy problem, which is what we've done, right? Particle in the box. Density of states goes like the square root of energy. So the higher the energy, the more states I actually have in a given energy range. But the other one that's kind of important is the density of states is proportional to the volume. And the reason you can see that, so A here is the length of the box, right? I have A squared, and then I take the power 3/2, so that's A cubed. So the density of state is also proportional to the volume. So if my volume goes up, I get more states. So do you remember what I told you in the beginning about entropy? So if I make the volume go up, the number of states goes up in a certain energy range. I think intuitively you may start to think what that's going to mean, right? If the number of states goes up, the entropy is going to go up, because entropy is related by kb log omega to the number of states with a given energy. The more states I have at the energy that I am, the more entropy. So if entropy goes up with volume, what does that mean? That means I have positive thermal expansion, right? That's what I just showed you in the beginning of the lecture. So this kinetic energy operator is clearly programmed to give you positive thermal expansion. And that's why we most of the time have positive thermal expansion. I'm going to need all kinds of other stuff in the Hamiltonian to undo this if I want to get negative thermal expansion. Let's put some numbers on this. Okay, let's say I put one particle in a box that's a 3D box that has a length of 10 centimeters. And what I roughly want to figure out what the density of states is at a typical energy range. So I have to sort of assume some energy, and it's maybe a little hard to guess, but I'm going to assume something of the order of the thermal energy. So I'm going to assume that it's 3 kT over 2. So the particle is of the order of the thermal energy, and it's an atomic light particle. So I took something with, I think, like 100 protons or so. So I'm going to assume that the mass is of order 10 to the minus 22 grams. And I now want to look at how many states are in a range of plus or minus 1% of this. So this is my average energy. How many states in the range of plus or minus 1 fluctuation? You could now calculate that by taking, you could actually do that by plugging into this equation. And what you find is that omega is of the order of 10 to the 28. So even for one particle in a box, you have an enormous number of states within a 1% fluctuation of the energy. This gets actually worse, well, worse or better, depending on perspective, if you put n particles in a box. So if you do n particles in a 3D box, right, what we did before, just to be careful, is one particle in a 3D box. So if you do n particles in a 3D box, I'm not going to solve them, but I'm going to write down what the answer is. Even in Macquarie, this is only sort of half-assed solved. Then the number of states with a given energy is 1 over the gamma function of n plus 1 times the gamma function of 3n divided by 2. And by the way, the gamma function is of n, is n factorial when n is an integer. But it's something else. It's in between when n is not an integer. Okay, times, this we're not done here, 2 pi ma squared over h squared to the power 3n over 2 minus 1 times the energy to the power 3n over 2 minus 1. And you could find this in Macquarie. Okay, let me write this here. So that stuff here is in Macquarie. I think it's in section 1.3. But maybe a few interesting things to look at. Again, you know, don't get confused by all this like numbers, right? This is the gamma function of stuff. But you want to look at the physical parameter dependence, right? And to be honest, the only physical parameter, there's only 2 physical parameters in here, right? It's n, which is the number of particles, and a, which sets the length scale of the box. And we again see the volume show up here, right? Because we have a squared to the power 3n over half. So this is basically the volume to the power n. So not only now does my number of states scale with n, it's like worse. It scales like the volume, but volume to the power of n. So I guess the simple person's view is here, there are many, many, many microscopic ways to get a certain energy. As n gets very large, as n gets over the order of Avogadro's number. So I think Macquarie does an analysis that if n is of the order of Avogadro's number, so if n is 10 to the 23rd, then the density of states goes like 10 to the power n. And that's an enormous number, right? Because you're doing 10 to the power of Avogadro's number. The really cool thing, and you should give that a shot, you know, you're going to feel so good if you make it work. We will later show that this statement leads to PV is nRT, or so PV is RT. And if you're smart, well, no, I'm not going to say that because then you don't feel smart if you can't do it. You could sort of see that coming because remember that this is going to relate to the entropy, right? The log of this is going to relate to the entropy. And you know, when you take logs, logs are brilliant, right? Because they make all the constant stuff go away, right? Because the log of a product is the sum of the logs. And then when the log of the thing is constant, then when you take a derivative, it all dies, right? It all goes away. So if you could relate entropy to volume, because volume is going to appear here and energy is going to appear here, right? You can get thermodynamics going. And again, if you're more than welcome to reserve that fun for later. But later we will do this. And later we will show that an ideal gas is nothing else but this. It is the statement of, it is the macroscopic version of n particles non-interacting in a box. That mathematical, that quantum mechanical statement leads to an ideal gas. Okay, let me do quickly a few things to warm us up for next lecture. So we don't have to do too much math in next lecture. And then you could also read about it if you don't know how to do this. So in statistical mechanics, we use a lot of binomials and multinomials. And you know what these are, right? This is all the, you've taken courses, I hope, in stat, one of your favorite high school courses, I'm sure. So this is, if you have n things, you know, it could be particles, states. If you ask the question, how many ways are there to divide n things into groups, in two groups? Sorry, into two groups. Okay. Into two groups, one of n1 things and one of n2 things, right? Where n1 plus n2 equals n. And you know the answer to that, right? Or you wouldn't have gotten here. That's n factorial divided by n1 factorial divided by n2 factorial. This is why I love teaching graduate students, because I don't have to explain this. And of course, you can write that as n factorial divided by n1 factorial divided by n minus n1 factorial, because the two groups are complete. So that's the binomial. The multinomial is the same thing, but with n groups. So the multinomial is, now you have, how do I take n things and I divide in n groups, and the number of elements in each group is, you know, n1, n2, etc., up to n small n. Sorry, I call this R later. Let me call this R for now. Otherwise, we have too many n's. Okay, and the combinatorial solution for that, as you know, right, is the number of ways to do this is n factorial over n1 factorial, n2 factorial, all the way up to nr factorial. And one more thing. In statistical mechanics, we will always take logarithms of these binomials. Okay, I go down, come on. Need to make the camera faster. We will always take logarithms of these binomials. And when you take logarithms of big binomials, there is something called Sterling's approximation that we will always use. And it's beautiful because you can get rid of the factorials. Factorials are a mess to do math with, right? Because it's hard to take derivatives of them. So for large n, Sterling says that the log of n factorial is, well, I guess I should say is approximately equal to n log n minus n. super useful. Okay, this will come back time and time again. So program it in your head. You can even try this on your calculator for as far as you can get, because n factorial blows up pretty fast, right? Like if you go to like 50 factorial, you won't even get there. But you'll see that this actually already works fairly well for relatively small n. But for the n's that we're going to use, like n is going to be of the order of Avogadro's number, this is perfect. This is essentially zero approximation. If you forget Sterling's approximation, think 3n, n log n minus n. You will always remember. Okay. I want to send you home with a tiny homework problem. I want you to prove that the binomial is maximal when n1 equals n over 2. Right? So this number is maximal when you pick the two buckets exactly the same. Right? Because when n1 is equal to n over 2, then n2 is equal to n over 2. And the way you do that, by the way, since law, again, how do you take the maximum, find the maximum of something? You take the derivative, right? And you set that equal to 0. It's a mess to take derivatives of factorials. So what you always do is you rely on the fact that the log is a positive function. So the log is maximal when its argument is maximal. So if I ask you to take the maximum of this, you can just as well look for the maximum of the log of that. And the reason that that's handy is because then I can use Sterling. Right? And then I get rid of the factorial. So Sterling is brilliant, right? If you have factorials in an equation that you need to optimize, you always take the log to get rid of them. So try that at home so that you play a bit with the math. If I have time, I'll start it on Monday as well. It's not that hard. And if you really want to push yourself, you can then prove that for a multinomial similarly is maximal when all the buckets are the same size. So when n1 is equal to n divided by r. And the same for all the other buckets. So the conclusion is sort of a binomial, multinomial, whatever, is maximal when the buckets you're dividing in have the equal number of things in them. Then you have the maximum number of ways to do that. Okay? Anyway, give that a shot at home, and then we'll pick that up again on Monday. So enjoy your weekend. Hopefully the smoke goes away and you can actually do something and get a walk in, get some exercise. It should get better. So I'll see you on Monday. Take care. Bye.